In this video, we'll start our discussion of inverse functions. Inverse functions is something that we actually do every day without even thinking about it. If you think about using your Google Maps to drive from your home to another location, and then maybe you're reversing that when you go from that location back to your home, right? You are reversing the operation that you just did. And so we're going to talk about what that means mathematically and what types of functions actually can have an inverse function. And then we'll actually go through the process of finding the inverse function and understand how they relate graphically, and then talk about a specific case where we have to restrict the domain to find the inverse of a function. So let me just introduce it in this way, that an inverse function is a function that takes us back to an original value before a function is applied to it. The inverse function reverses the effect of the original function. The following table gives us some everyday examples of inverses, just like I was talking about earlier. So if the original function is to open a door, what can you do to reverse that operation? Well, you can close the door, right? If the original function is to sit down, the inverse of that would be to stand up. If the function is to turn a light on, we can turn the light off. I mean, those are simple ideas, but it does get to the point of what an inverse function is. We applied some operation to take us to some location, and then the inverse function is going to be the operation that takes us back to the effect of not even doing that operation. So does every function have an inverse? Can we reverse every operation to get back to our starting point? Well, in real life, there are things that we can't undo. For instance, if we cut a piece of paper, you cannot get it back to its original form, right? I mean, you can tape it up and glue it, but it's not going to be the original piece of paper. If you crack an egg, you can't undo that to get the egg back into the shell. If you spill a drink, right, you can't get it back into the drink in the way that it was originally. So not every operation can be reversed. Likewise, not every mathematical function has an inverse function. But let's think about some mathematical examples. If I add a number, what would be a way to get back to the original number? Right, you can subtract the number, right? Like if I had the number 5 and I added 2 to get 7, well, I can start with 7, subtract 2 to get back to the original number 5. So if we subtract a number, the way to get back to the original number is to add that number back. We multiply by a number, we can divide by a number, assuming it's non-zero. If we divide by a number, we can multiply by a number. So here is a table that actually goes through some of these operations and trying to figure out how can we get back to that original number. Just like I was saying before, if we have the number 7, if I add 2 to that number, I get 7 plus 2, or 9. But now if I subtract 2 from 9, 9 minus 2 gives me 7, so I get back to the original number. If I have the number 5 and I multiply it by 4, I get 5 times 4, which is 20. But now if I divide 20 by 4, I get back to the number 5. If I take negative 2 and square it, I get 4. But if I take the square root of 4, I get 2. So this last example is a case where this operation is not invertible. When I square a number, it cannot be inverted to get me back to the original number that I started with. And so we're going to talk about what types of functions actually can be inverted, and that requires us to have this discussion of one-to-one functions. So first recall that a function is a relation in which each input corresponds to exactly one output value, right? I used the example of a vending machine. If I press a particular item, I should get only one item out of that vending machine. Just like with a function, if I input a value, I should get only one value out. And so consider the function f of x equals x squared. A table of ordered pairs and the corresponding graph are shown, but just recall this, that if we have a table of values from -2, -1, 0, 1, and 2, and I square each of those x values, I get 4, 1, 0, 1, and 4. And when we plot those on a coordinate system, we get this basic parabola that has a vertex of 0, 0, and opens up. It does pass the vertical line test, right, because every vertical line goes through at most one point on the graph. Well, the inverse function, the idea that we just talked about, is that the inverse function will reverse the operation that we performed. That is, if we start with a number, apply a function, and get to a new number, we should be able to apply the inverse function to get back to the original number we started with. And so there's this inverse or reversing operation that takes place. And so if y equals x squared has an inverse function, then we should be able to interchange the x and y values and obtain a function. So when the x and y values are interchanged, we get this following set of ordered pairs that I have in this table on the right. So on the left is the original table of values for y equals x squared. That is -2 corresponds to 4, -1, 1, 0, 0, 1, 1, and 2, 4. And so if I try to reverse those, then my y value would now become my x value. So now in this table I have my original y values in the x column, so I have 4, 1, 0, 1, 4. And in the y column I have the original x value that I had to square to get that y value. So that is -2, -1, 0, 1, and 2. But this is where I have a problem, because this resulting set of ordered pairs is a relation, right? That's just a set of ordered pairs, but it does not define a function, since the values of 4 and 1 each correspond to more than one output, right? 4 corresponds to -2, but 4 also corresponds to 2. 1 corresponds to -1, but 1 also corresponds to 1. So there is an input value of x that has more than one output value. For a function to have an inverse function, then what must be true is that each x value must correspond to a unique y value. The y values must not repeat. Now, for it to be a regular function, that's fine. The y values can repeat. But for it to have an inverse, we can't have repetitions in the y values either. And so this type of function is what we call a one-to-one function, where each x value corresponds to a unique y value. So the mathematical definition is that a function f is a one-to-one function if no two elements in the domain of f correspond to the same element in the range of f. Does that make sense to you? So no two x values, right? No two elements in the domain, so no two x values can have the same output value. So no two x values can have the same output value. So for a and b in the domain of f, such that a and b are not equal to each other, then their corresponding y values, f of a and f of b, cannot equal one another. Okay, so every value in the domain corresponds to a different y value. And equivalently, we can say that f of a equals f of b, that is, if two y values do equal, then it must be true that their input values are the same, that is, that a and b are also equal. Now we can determine from a graph if a function is a one-to-one function, and we use what is called a horizontal line test. If any horizontal line touches a graph of a function f in more than one point, the function is not one-to-one and does not have an inverse function. We can see here we have the graph of y equals x squared on the screen. Again, that goes through -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And that we notice that a horizontal line that is drawn through the line y equals 4 touches 2 points on the graph, right? So it's showing that the x value of -2 and 2 corresponds to the same y value, which contradicts the definition of a one-to-one function. So this is a function, it is just not a one-to-one function. And remember why we want it to be one-to-one. That means when we reverse the x and y values, we still get a function. But if there are two y values that are the same, when we reverse it, then those are now x values that correspond to more than one output value, which contradicts the definition of a function. So I know this seems a lot to take in, but we are really just talking about what types of functions have inverse functions, and those are ones that are one-to-one. One-to-one means that every input corresponds to a very different output, and we can determine if a function is one-to-one by the horizontal line test. So here's an example. We want to determine if each function is a one-to-one function. We first have this function denoted by the set of ordered pairs 4, 2, 3, 7, 5, 2, and 8, -1. This is a function because each input, 4, 3, 5, and 8, corresponds to one output value. But it is not a one-to-one function because notice that the value of 2 appears in two ordered pairs. 4 corresponds to 2 and 5 corresponds to 2. And if we wanted to do a mapping, like if I listed the x values in order from smallest to largest, so 3, 4, 5, and 8, and my y values, which are -1, 2, and 7, I notice that 3 corresponds to 7, 4 corresponds to 2, 5 corresponds to 2, and 8 corresponds to -1. So we see these values of 4 and 5 that have the same output value, which means that this is not a one-to-one function. What about B, f of x equals 3x plus 7? So y equals 3x plus 7 is an example of a linear function whose y-intercept is 7 and whose slope is 3. To recall, that means, I'm just going to do a rough sketch. If we have a y-intercept at 7, we would then have to go up 3 over 1, up 3 over 1 to get the graph of the line. And the main thing I want you to observe is that this line is a slanted or oblique line. And if we perform the horizontal line test, any horizontal line through the graph is going to hit at most one point on the graph. Therefore, this is a one-to-one function because it passes the horizontal line test. In example C, I have a graph of a polynomial function that has an even degree. And I know that because it's going up at both ends. I would also know that the leading coefficient is positive. I see that it has zeros of 0, 1, and 4, with 4 having a multiplicity that's even because it bounces off of the x-axis there, and the other two have an odd multiplicity. So I notice that it's starting up to the left, but then it's coming down through this origin to some minimum point. Then it goes back up through the point 1, 0 to some maximum point between the 2 and 3, and then it turns back down and touches the x-axis at 4, 0, and then goes back up. And so I'm wanting to find out, is this a one-to-one function. And if I draw a horizontal line through this function, notice that it touches more than 1 point on the graph. If I draw the horizontal line through 6, I hit 2 points on the graph. If I draw a horizontal line through 4, I'm hitting 4 points on the graph. So this is not a one-to-one function.